Hey everyone, and welcome. Today, we're diving into the 4 core principles of object-oriented programming. OOP. If you've ever found this topic to be a bit of a head-scratcher, you're in the right place. Stick around, because we're going to make it all click.
And look, you're definitely not alone. I love this quote from developer Khalil Stemler because it just nails this feeling so many of us have, right? You learn the definitions, you pass the test, but then you get out there and trying to apply it to real, messy software. Well, that's a whole different ballgame. So that really begs the question, doesn't it? Why is this concept, something so fundamental to how we build software today, often so tricky to really get? Well, to find the answer, we've got to go back and look at the problem OOP was designed to solve in the first place.
See, before OOP really took over, the main way to do things was called procedural programming. And it was fine for a while. But as programs got bigger and bigger, I'm talking from a few hundred lines of code to millions, just managing all the different parts became a total nightmare. A new way of thinking was desperately needed to handle this explosion of complexity.
Okay, so when you look at these two side by side, you can really see the huge shift in thinking. Procedural programming is like a recipe. It's a top-down list of instructions for the computer to follow. OOP completely flips that script. It's a bottom-up approach where you start by creating these objects that actually model things from the real world, bundling data and the code that works on that data together. And this change, well, it makes our code more secure, way more reusable, and a heck of a lot easier to manage.
And that brings us to the star of the show, the object itself. Think about programming a chess game. The old way? You'd have all these separate variables floating around, one for the knight's position, another for its color, another for if it's captured. It gets messy. But with OOP, you just create a single knight object. And that one thing holds all its related data, and it also knows how a knight is allowed to move. It's a neat, self-contained little package that makes perfect sense.
Okay, so we have these objects, which is great, but to make them really work in a big system, we need some rules. And that's where our first 2 principles come in: abstraction and encapsulation. They're all about making our objects easy to use from the outside while keeping them safe and sound on the inside.
Let's kick things off with an analogy that I think everyone gets. Your TV remote. You have this really simple interface, right? The buttons. You press volume up, the volume goes up. You don't need to know or care about the infrared signals, the circuit board, or the TV's internal receiver. All that crazy complexity is completely hidden from you. And that, right there, is the core idea of abstraction in programming. It's all about creating a simple, clean interface for our objects and hiding all the messy, complicated stuff inside. So in your code, you might just call a simple method like database.saveuser, and you can trust that it works without needing to know a single thing about the SQL commands or network connections happening under the hood.
And honestly, this is a total game changer. It means that as a developer using someone else's code, you only need to worry about what an object does, not how it does it. This separation makes code so much easier to reason about, to use, and to build on top of.
All right, now let's switch gears to a slightly different but related idea. Think about a washing machine. It has rules, right? A specific process. You can't just set its state to paused if the machine is still off. That doesn't make any sense. You can't just reach inside and start manually turning the gears. You have to use the buttons on a control panel. And that is encapsulation. It's the practice of bundling the data, like the washing machine's current cycle, together with the only methods that are allowed to change that data. So if abstraction is about simplifying the outside view, encapsulation is all about protecting what's on the inside. We make that internal data private, forcing everyone to go through the public methods, the object's buttons. And this is so crucial in big, complex programs. It's what stops our objects from getting corrupted or put into some weird, invalid state. It makes sure the object itself is the one and only source of truth for its own data, which helps us squash bugs and prevent all sorts of strange side effects.
All right, so far so good. We've got objects that are simple to use and their insides are protected. Now, the next 2 principles, inheritance and polymorphism, are all about making our code more efficient and way more flexible.
I really want to highlight this quote because it clears up a huge misconception. When we first learn about inheritance, we almost always see these examples like a dog is an animal. And yeah, that's true. But in the world of programming, the real superpower of inheritance isn't about perfectly modeling the real world. It's a practical tool for reusing code. So here's the bottom line. Inheritance is just a mechanism that lets a new class, a subclass, take on or inherit the properties and methods of an existing class, the superclass. It lets us write some common, shared logic just one time and then reuse it over and over in more specialized classes.
This makes way more sense with a real-world code example. Let's break it down. Imagine you write a base API class that knows how to do all the boring, common stuff for making requests to a server. Now, instead of rewriting that code everywhere, you can just create a users API class and a forum API class that both inherit from that base. They get all that common logic for free. All they have to do is add their own specific functions, like getting users or getting forum posts. It's incredibly efficient.
Okay, reusing code like that is super powerful. But our final principle, polymorphism, is what brings a whole new level of flexibility to the table. And it has a cool name too. It literally means many shapes or many forms in Greek.
And to really get this one, let's step away from the code for a second. Just imagine the role of a clerk at a grocery store. That role has certain responsibilities, right? They need to be able to scan items, bag them, and take your payment. The role itself is an abstraction, kind of like a contract for a job.
So you've got this clerk role, right? But think about who can actually do that job. You might have James, who does the job but is a bit snappy. Or Mariah, who gets it done but is kind of brooding. Then there's Max, who's super friendly. Even the manager, Mark, can step in and fill the role when needed. They all fulfill the duties of a clerk, but each one does it in their own unique way. They take on the same shape but have different forms.
And that, my friends, is polymorphism. It's the magic that lets you write code that just talks to the clerk role, and you don't have to care if it's James, Mariah, or Mark behind the counter. You can have a single function, process checkout clerk, and pass in any of those different objects. You call the same method, like clerk.scanProduct, and each object responds in its own special way. This makes our programs incredibly flexible and easy to extend.
Okay, we've gone through all 4 principles. So, what's the big payoff? Why do we bother organizing our code this way? Well, it all comes together to help us build software that's more robust, easier to change, and just simpler to live with. Let's do a super quick recap. Abstraction hides complexity so we don't have to think about it. Encapsulation protects our data from being messed up. Inheritance lets us reuse code so we don't repeat ourselves. And polymorphism gives us amazing flexibility. You put all that together, and what do you get? Code that is just easier to test, way more flexible when things change, and so much simpler to maintain in the long run.
But, it's also important to remember that nothing in tech stays still. As this quote points out, it's from a pretty dense research paper on something called the phi calculus. Even an idea as big and dominant as OOP is still being studied and formalized. We're always looking for better ways to build things.
And that kind of leaves us with one last big question to chew on. OOP was this massive shift away from procedural programming because we had a new massive problem, complexity. So what comes next? What's the next big problem we're facing that's going to demand a whole new way of thinking about how we write our software? Something to think about. Thanks so much for joining me.